Hello, everyone. We're going to start. Well, I guess we'll just start now. It's 1 minute after the hour. Welcome to the Air-Sea Fluxes from Space webinar series. Today, we have Sarah Nicholson from CSIR in South Africa, and she's going to talk about the impact of storms on CO2 and heat exchange across the Southern Ocean. I'll let you take it away, Sarah.
Thank you. Thank you, Sarah. I hope everyone can hear me okay. Eventually, I hope everyone can see my screen.
Yep.
Okay. Okay, so sorry. First of all, I just want to say thank you so much to Sarah for extending the invite to present on this webinar series. Yeah, I won't be talking too much about Air-Sea Fluxes from space, but more from bottom up, from in situ observations. But yeah, I am going to take you through a series of studies which are mostly based on glider observations, which I think make a good case for really shining a lot more light on the role of storms in CO2 and heat exchange in the Southern Ocean. And of course, the work that I'm going to present now is really a massive team effort. There's a few of us that are really interested in understanding how storms are modulating CO2 and heat, and I've listed some of their names there. And then, of course, there's other members of the community that are, of course, interested in this. I'm from a research group called the Southern Ocean Carbon Climate Observatory. As Sarah mentioned, it's based in the CSIR in Cape Town, South Africa. Right. So, I mean, this is no news to, I'm sure, many people in the room. Can I just ask a quick question? Can you see my mouse?
Yeah.
Okay, perfect. Okay, good. But of course, the Southern Ocean is a key player in modulating global climate, and that's through its disproportionate role in taking up CO2 and heat. And so I've written some of the numbers here. It's significant, it's important, and that's why we study the Southern Ocean. And this animation here is one of those classic reconstruction, CO2 flux reconstructions based on some ship observations. It's called the CSIR ML6, so it's come from our research group, and very nicely you see this big blue band of CO2 uptake in the Southern Ocean. But you also do see the sort of modulation, seasonal modulation of outgassing coming in there as well. But we've got some big issues. It's really difficult to observe. It's really difficult to project how this role of the Southern Ocean and CO2 and heat uptake is going to change in the future. And there's a few reasons why it's difficult. The first is, of course, Earth system models. State-of-the-art Earth system models aren't without fault. There are significant biases, particularly in the Southern Ocean. So I just have a few examples of that. So there's sea surface temperature biases that are largest in the Southern Ocean. There's significant variability, or sorry, uncertainty between models. And probably one of the more striking things is, this is from a CMIP5 model, but this is looking at the seasonal cycle of CO2 fluxes in different model configurations shown by the color lines. And the black line is the observations. And this is work from Precious Mangwe, who was also from SOCO. And it really does highlight how the models are struggling, right? Models are struggling to get the seasonal cycle right. But it also does raise one question, in that, can we trust this black line? And so this black line is a reconstruction based on ship data. And of course, Southern Ocean is extremely poorly sampled. There's not a lot of ships going into the Southern Ocean, particularly in winter. So there's some significant seasonal biases. So the question really is also, can we trust this black line? Can we trust the observational constraints, which are, unfortunately, in the Southern Ocean, quite weak? The third thing to consider is that, and where I'm going with this talk, is that actually the ship-based observations and the models are all lacking in resolution. So the models are coarse, classic 1 degree, sometimes a little bit higher, but really coarse resolution models observations primarily based on ship, but of course with SOCOM coming on board, we have an increase in resolution, so that's really helped things. But you know, we are really not resolving the high frequency fine scale variability that we know is dominant in the Southern Ocean. We know that storms are prevalent. It's literally the stormiest place on the planet. And the storms are very strong, often, you know, reaching category hurricane status. When you look at the ocean itself, it's very turbulent. And so when you look at how different resolution models are resolving that turbulence, you can see that coarse resolution models are already missing all of the mesoscale and submesoscale variability that we know to occur there. Using some satellite observations, so we can get an idea of, well, how important do we think these subgrid scale processes are that we're missing in the models? And so basically everywhere you see is green in this map, it's where subgrid scale or high frequency variability is sort of dominating over larger scale, more seasonal scale variability. So it's really quite prevalent. And you can see that it matches quite nicely with the sort of underlying mesoscale, submesoscale field. So these storms are not just passing over as wide swaths, but they're actually interacting with this submesoscale field. Okay, so SOCO, Southern Ocean Carbon Climate Observatory, we have been really interested in getting into this problem of how fine scale dynamics are important, you know, obviously in modulating CO2, but in a larger scale climate. And so SOCO has taken 3 different approaches. The first is really to get a lot of high resolution observations. So we've used gliders to do that. We also do a lot of ship-based observations, and you know, the ship-based observations are being brought into the SOCAT dataset, which is then developed where we're developing this reconstruction product, which is now one of the reconstructions that feeds into the IPCC. And kind of some of the thinking is to get the higher frequency data going in there, but that's just one aspect of it. The other aspect of tackling this question is to have a series. We have a series of forced biogeochemical models at various resolutions, at various configurations. And that is also helping to get some insight into the problem. But today I'm just going to focus on this aspect, which is this high resolution observations that we've been collecting. And we've been doing it for a number of years. So the SOSEX experiment is the Southern Ocean Seasonal Cycle Experiment, which I think most of you may or may not know Sebastian Swart. When he was at SOCO, he kicked off the SOSEX experiment with Pedro Monteiro. And I stepped in around 2017, 2018 with Pedro Monteiro again, and continued that work. So it's been a long observation. It's been a long program. I think what's been quite interesting and fun, I guess, with the SOSEX experiments is in about 2015, I think it was the first deployment, we started coupling the platforms. So we would couple a wave glider to a buoyancy glider as close as we possibly can, get them to sample. And that was really useful in that it helped us to really connect the ASC atmosphere processes to ocean mix layer, the boundary, ocean mix layer boundary, to a deeper ocean interior, and really try and understand, you know, and integrate those different processes. And then we also started in around 2017 what we call the SOSEX storm experiments. So we invested in some microstructure capabilities and have now collected around 5 months of microstructure turbulence data on the platform. So that's also been really interesting, challenging. Yeah. So now what I'm going to do is, so what I haven't mentioned is that we've occupied predominantly actually the subantarctic zone and the polar frontal zone along this Good Hope line. So this is the line that South Africa's polar vessel goes down to Antarctica, and we have a resupply vessel, and so we have this opportunity to deploy gliders. And so typically we deploy them, well, we have only deployed them along the Good Hope line, and more recently in the marginalized, and that's really in collaboration with Sebastian Swart's group, Polar Gliders. And so, yeah, so what's nice is actually that we've got these, we've built this data set in these 3 different, quite regionally distinct sites along the meridional overturning circulation, and I've sort of highlighted them here, so you can see that they're already characterized by quite different surface mixed layer properties and subsurface properties, and of course also just forcing. And so I'm going to talk about a few of these sites, and talk more about CO2 and heat. And I didn't mention, but yeah, of course, they have very different depth sections of a carbonate system, of DIC in this case, yeah. So I didn't say this also, but I'm going to take you back a little bit and then into more recent stuff. So just taking you back to the very first wave glider deployment we had in the Southern Ocean, and I might be incorrect, but I have feel like it might have been the first wave glider deployment. Can't say for sure, but it was in 2013, so it was really early days in terms of wave gliders. And so blue line is the flux of CO2, and orange line is the fugacity, which is PCO2 essentially. And you can see that over the 4 months that the wave glider sampled, this region, sorry, I haven't shown this map on the left-hand side, is once again a little bit complicated to explain, but just where you see blue is where intraseasonal variability dominates, and when you see red is where seasonal variability dominates. So it's kind of in a region where we would expect a bit of intraseasonal variability to dominate, sort of like a little bit more bluer. And so we do see this. We do see a lot of interseasonal variability. And in this conical paper, we link, well, Pedro links this variability to the passage of storms. But they also go ahead and ask this question about what temporal resolution do we need to accurately get the mean? So I've just said in the beginning, in earlier slides, I've said that, you know, we have a very coarse resolution observations from ships. And so this was really looking to see, well, what is the effect of not sampling at high frequency resolution? And in this figure, they do a subsampling of, in this case, it's the FCO2. They subsample it in quite an iterative way. So they subsample every hour. Sorry, they subsample at different intervals. And depending on that interval, they shift the sampling. So it's done in quite a particular way. But anyway, the point of this figure is to say, you know, as the cone increases, your chance of getting the mean decreases. And so really what they show in this paper, particularly in these blue regions, is that you need to really have quite high resolution data to reduce the uncertainty to less than 10%. And now what was interesting, and kind of where I have sort of stepped into, is trying to understand the response of the storms in the mixed layer, and trying to understand the phasing of these storms. So they put this in this paper, they put together this conceptual configuration showing the sort of various phasings. And we were quite interested in understanding, you know, there's different things that impact FCO2, and there's different things that will impact KW, which is the gas transfer coefficient, which I'll get into. And well, it's wind. And we wanted to know, is the wind and the response of delta PCO2 in phase? And if it isn't, what does that mean? So we had Kesha Tulsi, who's a PhD student who actually just submitted her thesis on last week, Friday. She really dug into this question about the phasing of KW, the gas transfer coefficient with the wind. So the flux of CO2 is based on the solubility, KW gas transfer coefficient, and the delta PCO2, which is really the focus. And this delta PCO2, so the reason why we're interested in addressing this is because we have high frequency wind variability from satellite. We have pretty good, and from reanalysis products, we have pretty good resolution with wind. but we don't have good resolution with delta PCO2. So we want to understand a few things. We want to understand, what does it mean if you don't resolve delta PCO2 correctly, if you don't have this high frequency response? And yeah, and basically just understand a little bit more about the mechanisms. So this was another really nice time series, also in the subantarctic zone from 2015 to 2016. And on the top panel, I'm showing you wind stress, which was observed from the wave glider. On the middle panel, upper ocean stratification with the mixed layer in yellow. So you see quite a nice seasonal cycle, deep mixing in winter, sort of re-stratifying events through going into from spring into summer, and then a very strong stratification in summer. And then this black line at the bottom is the PCO2 in the ocean, and you can see it's quite variable. Interestingly enough, not too much of a seasonal cycle. And then the color lines are the decomposition of PCO2 into thermal and non-thermal, which I apologize that I haven't explained that, but maybe if that comes up in a question, I can. Anyway, and so I'm just going to pick on three particular events which stood out. These are three events in summer where we had strong winds here, and we had quite a significant response in PCO2. And to really get at this question of the relevance of this high frequency delta PCO2, we did this little experiment where we set, sorry, here it is. We set, so this is orange line is delta PCO2. This black line here is the gas transfer coefficient is Kw. And then the flux is this black line, and then this blue line I'm going to talk about now. So what we did in this particular study is we set delta PCO2 to the pre-storm value, and we allow it to be constant. So it just basically is a filtering approach to removing this high frequency delta PCO2 value variability. And then we calculate the flux, and we get this blue line. So the black line is the actual observed flux, and the blue line is the flux if we only took into account a response of Kw, just assuming that there was not too much change in the delta PCO2. And what we see is actually that the uptake ends up being overestimated if you just consider Kw alone, right? So if you are an observing system that's calculating fluxes based on ship observations, and you're using high frequency wind, you may overestimate the uptake of the Southern Ocean. Yeah. Okay, so we went a little bit further. So that was just an example of spring. And then, of course, we did the same experiment, so Kw at the top, FCO2, and then the blue line representing the same blue line, and then the difference between the two. And this is we in this paper, we call it the PCO2 feedback, but basically it's just showing that there's a seasonal sensitivity of the response of delta PCO2 to storms. So you see actually the most, it seems like the strongest signal is from the winter to spring period. And then we have a sort of decrease in that during in summer when you have strong stratification. So it was interesting to see that, and then that study raised several other questions regarding understanding more mesoscale sensitivities to this effect. So anyway, so that's the paper. It needs more citations, so please go and have a look at it. And so we were interested on the back of that work to understand if there was some, understand whether or not what we were seeing in the observations, whether there was mesoscale sensitivity to that. And so in Tesha's PhD, she looks at using a model to do this. We had a model run with varying strengths of storms. And I'm just showing you like a quick snapshot of this because it's still in preparation. So we're hoping to submit this quite soon. But the point is that looking at, this is the anticyclonic event she looked at. So here it is. This is like a Hofmüller plot. And you can see that there is an increase in the contribution of FCO2 within the eddy, starts on the edges of the eddy, within the eddy. And we see mostly it being blue, so it's really counteracting the FCO2 uptake. And I guess I won't go into too much detail. We also have some observations more recently, not quite in the subantarctic zone, a bit north, and that points at sorts of similar sensitivities. So this was a wave glider data set that got sucked into well, actually it didn't get sucked into an eddy, but it followed buoyancy gliders that got sucked into the eddy. And so you can see it following this sort of circular pattern. And this first panel that I'm showing you is, once again, black is the flux. So this is the region of strong uptake, not even an ounce above the 0 line. And this blue is, so this is this approach to get to the relevance of each of these terms is different to the study before. This is based on a Reynolds decomposition, but I'm just showing you the percentage contribution of delta PCO2 to the flux in blue, in this, in purple, in this purple shading. And what you notice is in some periods, even under, so this is wind speed, even under moderate wind, you still have a significant contribution of delta PCO2. So it's not completely being saturated by the wind through KW. Of course, there are events like this one, where the contribution is much smaller relative to KW. But we're interested in these sort of moderate to strong winds. And this particular case, we see, so this is when the wave glider was moving into an eddy. And black line here is density and its temperature and salinity in the different colors. But anyway, just very quickly, you can see this, the sort of feature, sort of density gradient here. And you see, so this bottom panel is ocean PCO2 in black line, and then the decomposition into the thermal and non-thermal components of PCO2. And so you see, very interestingly, you see the sort of bump here, which matches up with the density variability, which we knew was as the glider was crossing on the edge of an eddy. There are other interesting features, but anyway, so this is work that's being explored by our MSc students between soccer and polar gliders, Gonzalo, and so we're digging into the mechanisms a little bit more also. Okay, last CO2 study, and then I'll talk a bit about heat. So this is moving further south now, away from the subantarctic zone into this band of outgassing that I spoke about earlier. And so this band of outgassing is really driven by large-scale Ekman transport, which drives this upper circumpolar deep water, which is rich in DIC, up to the surface, and then, of course, impacts the delta PCO2 gradient and causes an outgassing. It also happens to coincide with storms, with the increase in the distribution of storms. So this is around 54 degrees south, which is where we had the gliders. And we were interested in understanding what role the mixed layer plays in modulating between, the ASC or the wind events and the reservoir of DIC. The mixed layer being this like critical boundary between the two. So it's actually quite an old study now, but anyway, so time flies. So this is some results from the glider observations that we took. So this is, well, it's frictional velocity cubed, which is essentially, you can think of for now the wind, but it's related, frictional velocity is related to mixing. So this is now the Sussex storm experiments that I spoke about, where we've started to integrate now turbulence sensors onto the gliders, because we really recognized that we needed to understand, the sort of storm-driven mixing to answer some of the physics questions. So this is TKE, it's a dissipation of turbulent kinetic energy. The third panel is salinity, which we are thinking of as a passive tracer in this case to understand sort of entrainment events. And then we've got delta PCO2 once again, which you'll notice is fluctuating very much between in-gassing and out-gassing, and then FCO2, the flux at the bottom. And I'm highlighting two events that were really interesting in this particular case, where we had two quite prominent entrainment events, which resulted in two of the more significant outgassing events. And it was at a time where the mixed layer was tightly coupled to this reservoir, subsurface reservoir. And then we had a sort of a period of a more quiescent period, less storms, and also quite strong heat flux. And so we see the mixed layer decoupling away from that reservoir as it shoals. And interestingly enough, we have this other event with another strong storm, but it doesn't really result in the magnitude of the delta PCO2, and in fact the flux is very small. And this variability that we see here, in the paper, which I'm not showing here, we've linked to lateral advection, wind-driven lateral advection. And so the purpose of this paper is just showing evidence that really storms can tap into this reservoir and drive quite significant outgassing events. And unfortunately, I didn't write the numbers here, and it's been a while, but these two events had quite a big impact on this mean period. This was over summer. Sorry, I'm forgetting to mention important details, but this was over a summer period, austral summer period. Yeah, so this was just relating using wall of law scaling to relate the wind to the dissipation. So it just says that wind is important driving the surface mixing. Okay. Oh, and so what's really cool? So we have more evidence for this. This is a paper by Magdalena using floats, but across the whole of the Southern Ocean, and has also shown that storms are driving outgassing. So it's really cool. Okay, so now moving away from CO2, and the last two studies I'm just touching on are more around heat. And so this is work that Marcel Duplessis has led, and we currently have it in review. And it's really looking at this, earlier I mentioned that there were some SST biases in climate models that were quite bad in the Southern Ocean. And, you know, quite often this is attributed to the misrepresentation of clouds. And in this particular case, we're sort of hypothesizing that misrepresentation of that in fact is due to a misrepresentation of mixed layer processes, and that's due to insufficient vertical resolution. So this is a cool study that shows the effect of increasing ocean vertical resolution. And then the second is that, of course, 1 degree model, Earth system models are not going to resolve storms as well as they should either. And so when you look at the difference between CMIP6 and ERA5, we see quite a lot of blue. So CMIP6 models are underestimating the number of cyclones that should be present in the forces. So using the same glider observation data set I just spoke about, but from a CO2 context, Marcel has been looking at understanding sea surface temperature changes and relating them to storms. I thought this was a really neat animation of the glider, of the storm passing over the glider, and you can kind of see where the eye of the storm is and the strength of the wind. But anyway, so the storms are doing two things in terms of surface temperatures. Of course, they are driving entrainment, so they are tapping into a cool reservoir of water, but they are also and so they're also deepening the mixed layer, which impacts the effective heat capacity of the mixed layer. It's harder to warm up a deep mixed layer. And the other thing is when you don't have storms, the mixed layer can shoal, and you shallow the mixed layer, which makes it easier to heat up. So it's more responsive to air seed processes. And so in this paper, we make the case that looking at the frequency of storms is important for setting the warming rates of summertime surface temperatures. And we've done this analysis on a Southern Ocean scale, looking at counting the number of storm days in summer, and looking at the correlation between shallower and deeper mixed layers, and the correlation between the maximum SST. And you see that there is some relationship there. Yeah, so I guess in this work, the hypothesis is that possibly we see that these climate models have too few storms, so it's possible that there's less mixing, shallower mixed layers, and warming rates that are too high. So that's a bit of work that we are currently revising, and yeah, so watch the space. And then this is the final piece of the puzzle, but it's not actually a piece of the puzzle. This is bits of information spread across the Southern Ocean. But this is a really nice study by Isabel Giddy, and this is moving further south into the marginal ice zone. And in this particular case, we were interested in understanding the winter water. And for the benefit of you that maybe don't know what the winter water is, it forms in wintertime under destabilizing buoyancy forcing. And it's when you have a lot of ice formation, it's very cold water. And then in summertime, you have heat flux that caps the surface mixed layer and warms up the surface mixed layer. So then you end up with this inversion where you have a warm surface mixed layer, the winter water, and then this upper circumpolar deep water. And the upper circumpolar deep water, this region in the south is really important because it's on its way to being transformed into Antarctic intermediate water. And it's really the exchanges of properties across the winter water that allow for that transformation. So we were interested in understanding, what is driving the erosion of winter water through summer. So when you look at this is based on some climatological mean data from EN4. This is the winter water thickness. And this is the change in the winter water over summer from a climatological perspective. So you see it gets thinned out by about 50 meters in places. So once again, we had our gliders out there in summertime, and you can really nicely see this cold tongue of winter water sitting on top of the warm surface water and the warmer UCEW. So this is temperature. The next panel is stratification with depth. And then this is again another section of turbulent dissipation. And what was really interesting, okay, so some characteristics of the winter water. We see that the thickness reduced by around 36 meters over these observations. And we saw that the winter water was in fact increasing in temperature. And so there's two interesting observations from the mixing observations. The first is these strong wind events that drive mixing. So once again, storms coming in, and we see quite a strong relationship between the surface observation of epsilon to to wind. So law of the wall scaling is, seems to work well here. And then in the subsurface, we see this other band of raised dissipation, which we were really interested in trying to understand what that could be. And so that's really the question is, well, what's driving the subsurface mixing? And yeah, so when you have, okay, so I guess the answer in short is what we think is double diffusive convection. And this is really a classic property of having the sort of winter water sitting on top of UCDW, of sitting on top of this warmer, saltier water, this colder, fresh water. And what happens is if a particle is displaced downwards, heat diffuses much faster than salt. And so it gains heat and then bounces back up. And so you end up with these classical staircases, what we see. This is salinity and this is temperature. And we see these classical staircases forming on the temperature. There's so in this paper, we presented 3 different lines of evidence. The other one is looking at density ratios, and DDC is typically in this region. So we once again get confirmation in the subsurface layer that it could well be DDC. And then a third is looking at spice, so looking at the variations along ice spignals. And increased spice would be connected to increased DDC. And so there seems to be evidence from these observations that it is connected, this increased dissipation is connected to double diffusive convection. And so finally, when we were interested in understanding what is driving the erosion and warming of this winter water layer, when you put the pieces of the puzzle together and you look at the heat flux, you see there's a downward gradient of mechanically driven or wind-driven heat going from the surface mixer into the winter water. And then there's an upward gradient transport of heat through what we think is through DDC. And yeah, I think it's more evidence. Okay, so the DDC was super interesting. I also think it's more evidence to say that, storms are potentially really important in driving heat down to the winter water and modulating the water mass transformation. Sorry. Okay, and so this is Isabel Giddy's paper. It's fantastic. You should go and have a look at it. She did a really great job. Yeah, so I guess I've shown you lots of studies, and maybe it's overwhelming. I think my overarching point is that, I think that we need to try and figure out ways of resolving storms. They seem to be important. I think floats have definitely been helpful. But I do think, thinking about, for instance, this network, at the moment, all of the USV, uncrewed surface vehicle people are getting together, and we are pushing to really have a more coordinated, integrated AC flux observations from these platforms. And I think that will be really important in trying to, on a bigger scale, trying to really get a handle of how storms are modulating, and in fact, how storms are interacting with mesoscale fields and submesoscale fields and how they're modulating fluxes. I spoke about CO2 and heat in quite a separate way, but of course, I think that we should really also think about them. They are important for one another, so we should really think about them together. And then, of course, yeah. So then my final slide is just to say that I think all science is not without pain, and it's been really fun. It's also been extremely challenging. We've had a lot of crazy times. Working with gliders, it can be really fulfilling, but really stressful. This was just an example of an emergency recovery by this yacht that we had, and the yacht happened to pick the wave glider up in the middle of a storm, and they had to go hove to, and they had a whole bunch of amateur sailors on board that were extremely stressed out, and it was a lot. And that's all of them drinking a beer the next morning in Table Bay once they've just arrived, and there's the wave glider strapped on. And that was a wave glider that we just had communication issues with the sub, and so we couldn't, Anyway, and we've also had a wave glider that lost its subunit and drifted for 188 days to sea until we could get a fishing vessel to recover it on Kerguelen Island. So, but anyway, it still collected data, and so it was still interesting. But yeah. Anyway, so that's all from me. Thank you very much for listening.
Thank you so much. So, questions for Sarah? Maybe while people are thinking, I'll ask a quick question. Oh, I see Mara has her hand up, so let's start with Mara.
Yeah, thank you, Sarah. That was a really nice talk. I was wondering, I guess going back all the way to the beginning, where you showed the map of the green and blue showing areas of scale versus small scale dominance. I guess I was wondering, is there a connection between that and what you were talking about with storms? And maybe another way to formulate the question is how much of that, when you're talking about the large versus small scale variability has to do with atmospheric forcing versus intrinsic ocean processes.
Yeah, so that's the big question. So we've managed to observe that quite well from, so that was based on ocean color, which you have, 8 days, you can start to look at intraseasonal variability. It's quite difficult with the physics, right? Like it's difficult to look at mixed layer variability on those scales and make connections between that. But for sure, the hypothesis is that intraseasonal variability is being driven by storms and by meso and submesoscale processes. So, but yeah, I guess it would be nice to think about a way of really pinning that down. And yeah, sorry, I don't know if that actually is that sufficient?
Yeah, thank you. Yeah, it was just nice to hear your thoughts on that.
Okay. Yeah, cool.
Questions? Can I ask, you showed the differences between the climate model and ERA 5 numbers of storms. But you also had wave gliders out in the midst of these storms. How well does ERA 5 do at capturing what you see with your in-situ observations?
It's not bad, actually. It's oh gosh, I mean, we've got a few studies that have done the regressions, and it's not terrible. I think if I'm just trying to remember, and maybe if there's colleagues in the room that can correct me, but I want to say that it underestimates the magnitude, but it's pretty good at getting the phasing right. It's not bad, and that's why I guess I was making that point with, with Error 5, we can get to KW okay. We have hourly Error 5 data. The trick is really getting the gradient of PCO2. Yeah.
Are your gliders on the GTS? Are they feeding into ERA 5? Are you feeding into the analysis?
They're not. We need to do a lot more with our. We need to do a lot more. And that is an interesting point. No.
So they're independent.
Yeah.
So, I mean, you can paint a good story either way. And sometimes the challenge is just figuring out whether they're an independent data set or whether they are contributing to the analysis and reanalysis.
No, they're not. They're not contributing. No, they're independent. Yeah. But we've got there's 2 efforts at the moment because we've collected substantial amount of buoyancy glider data. There is an effort now to release all of that data and publish it in actually, I suppose in a scientific journal, to look at interannual variability and connect that a bit more. But yeah, we're getting there.
Other questions?
Cool. Maybe I've overwhelmed everybody with too many studies. Sorry, I might have raced through it also.
It was great. If I can just keep asking then, because this is air-sea fluxes from space, and so and satellites, of course, have different constraints in what they can measure. You've looked really closely at temporal sampling requirements. What do you think is so satellites are typically on a sun-synchronous orbit. You get at most 2 measurements a day, 12 hours apart. How limiting is that?
2 measurements a day, 12 hours. I mean, that's pretty good, right? I mean, if you can, but is that at a given location? At the same location?
Globally, if you have a sun-synchronous satellite, it measures, for example, at 6 a.m. and 6 p.m.
Yeah.
So the best you can do is 2 measurements a day, and you've skipped some usually.
Which I think is really good. I think the challenge is moving away from,
if there's storms that are really fast moving, are you missing something critical in that?
Yeah, fair enough. I mean, you're always missing something until you get to like instantaneous measurements, right? So, but I mean, I think in terms of being of reality and what we can achieve, yeah. But actually, it's a good. I haven't, to be honest with you, I haven't given it enough thought. I've been more in the in situ space, thinking about how we need to improve our observations from that perspective. But of course, yeah, that is also another thing to think about. I feel like, wasn't there there was a project that was going to be led by, oh gosh, I'm not going to remember it now. Never mind. Sorry, it was another American colleague, Zephyr or something, or anyway, never mind.
Beth Zippel, maybe? No? Oh, the satellite
Yeah, I think
proposal.
there
Yeah,
were,
SOS Zephyr. That was Joellen Russell, who
yes,
was the PI for that.
yes, Julia, yeah,
Yeah.
thank you. Yeah. That was that not looking at that sort of question, if I
That was,
recall, I don't know.
yeah, it was trying to get better wind measurements with a focus on retrieving in the Southern Ocean. And
Okay, yeah, okay, cool.
yeah, and I think although that proposal was didn't move forward, and I think that thought still continues that if we could get better wind measurements, especially in the Southern Ocean, at least we could get better statistics on extreme events.
Yeah.
But probably not seeing every guest. So we're back to these questions. What are the real sampling requirements? If you could have all the resources in the world, what would we want? What would be the minimum?
Well, I mean, it's quite interesting. So we're starting to think about waves a bit more, getting wave measurements on the gliders, just because, and also thinking about how the wind, if we're sampling at 0.7 meters off the surface, how wind observations are being impacted by wave shadows, and yeah, we're thinking a little bit more about that. And of course, waves being really important for mixing in the Southern Ocean also. Yeah.
Well, are there other questions?
Quiet.
If not, we'll wrap up. Thank you so much for a really nice talk.
Cool. Pleasure. Thank you so much for inviting me. And then, yeah, thank you everybody for taking the time to listen to me.
Yeah, thank you.
Thanks.